Thank you for pressing play. Your presence here brings joy to my heart. Thank you for joining us today as we dive into preadditive category. In mathematics, specifically in category theory, a preadditive category is another name for an ab category, i.e., a category that is enriched over the category of abelian groups, ab. That is, an ab category Celsius is a category such that every hom-set hom-ab in Celsius has the structure of an abelian group, and composition of morphisms is bilinear, in the sense that composition of morphisms distributes over the group operation. In formulas, FGH, FG, FH, and FGH, FHGH, where plus is the group operation. Some authors have used the term additive category for preadditive categories, but this page reserves this term for certain special preadditive categories. See below. In this part of the video, we'll be delving deeper into examples and analyzing its key components. The most obvious example of a preadditive category is the category ab itself. More precisely, ab is a closed monoidal category. Note that commutativity is crucial here. It ensures that the sum of two group homomorphisms is again a homomorphism. In contrast, the category of all groups is not closed. See medial category. Other common examples: category of left modules over a ring R, in particular. The category of vector spaces over a field Kelvin. The algebra of matrices over a ring, thought of as a category as described in the article additive category. Any ring thought of as a category with only one object is a preadditive category. Here composition of morphisms is just ring multiplication and the unique hom-set is the underlying abelian group. These will give you an idea of what to think of. For more examples, follow the links to below. Brace yourself for a captivating discussion on elementary properties as we explore its nuances and implications. Because every hom-set hom-ab is an abelian group, it has a zero element 0. This is the zero morphism from A to B because composition of morphisms is bilinear. The composition of a zero morphism and any other morphism on either side must be another zero morphism. If you think of composition as analogous to multiplication, then this says that multiplication by 0 always results in a product of 0, which is a familiar intuition. Extending this analogy, the fact that composition is bilinear in general becomes the distributivity of multiplication over addition. Focusing on a single object in a preadditive category, these facts say that the endomorphism hom-set hom-A is a ring, if we define multiplication in the ring to be composition. This ring is the endomorphism ring of A. Conversely, every ring with identity is the endomorphism ring of some object in some preadditive category. Indeed, given a ring R, we can define a preadditive category R to have a single object, let hom be R, and let composition be ring multiplication. Since R is an abelian group and multiplication in a ring is bilinear distributive, this makes R a preadditive category. Category theorists will often think of the ring R and the category R as two different representations of the same thing, so that a particularly perverse category theorist might define a ring as a preadditive category with exactly one object in the same way that a monoid can be viewed as a category with only one object, and forgetting the additive structure of the ring gives us a monoid. In this way, preadditive categories can be seen as a generalization of rings. Many concepts from ring theory, such as ideals, Jacobson radicals, and factor rings can be generalized in a straightforward manner to this setting. When attempting to write down these generalizations, one should think of the morphisms in the preadditive category as the elements of the generalized ring. In this section, we'll be deep diving into additive functors, unraveling its complexities and uncovering valuable insights. If Celsius and D are preadditive categories, then a functor f, C, D is additive if it too is enriched over the category ab. That is, Fahrenheit is additive if and only if, given any objects A and B of C, the function f, homo, b homoph, is a group homomorphism. Most functors studied between preadditive categories are additive. For a simple example, if the rings R and South are represented by the one-object preadditive categories CR and CS, then a ring homomorphism from R to south is represented by an additive functor from CR to CS, and conversely. If Celsius and D are categories and D is preadditive, then the functor category D is also preadditive, because natural transformations can be added in a natural way. If Celsius is preadditive too, then the category addic, D of additive functors and all natural transformations between them is also preadditive. The latter example leads to a generalization of modules over rings. If Celsius is a preadditive category, then modic addic, AB is called the module category over Celsius. When Celsius is the one-object preadditive category corresponding to the ring R, this reduces to the ordinary category of left-arm modules. Again, virtually all concepts from the theory of modules can be generalist to this setting. As we transition to the next segment, let's unravel the mysteries surrounding linear categories and gain a fresh perspective. More generally, one can consider a category enriched over the monoidal category of modules over a commutative ring, called a linear category. In other words, each hom-set homer, be in as the structure of an module, and composition of morphisms is bilinear. When considering functors between two linear categories, one often restricts to those that are linear, so those that induce linear maps on each hom-set. In the upcoming section, we'll be dissecting biproducts and exploring its intricate connections to our topic. Any finite product in a preadditive category must also be a coproduct, and conversely. In fact, finite products and coproducts in preadditive categories can be characterized by the following biproduct condition. The object B is a biproduct of the objects A. N if and only if there are projection morphisms Pj, Bj and injection morphisms Ij, a Jb such that type N is the identity morphism of B, Pgj is the identity morphism of a J, and Pgk is the zero morphism from a K to a J whenever J and K are distinct. This biproduct is often written as N, borrowing the notation for the direct sum. This is because the biproduct in well-known preadditive categories like AB is the direct sum. However, although infinite direct sums make sense in some categories, like AB, infinite biproducts do not make sense. See the biproduct condition in the case N0 simplifies drastically. B is a Newary biproduct if and only if the identity morphism of B is the zero morphism from beta itself, or equivalently if the hom-set hom is the trivial ring. Note that because a Newary biproduct will be both terminal Newary product and initial Newary coproduct, it will in fact be a zero object. Indeed, the term zero object originated in the study of preadditive categories like AB, where the zero object is the zero group. A preadditive category in which every biproduct exists including a zero object is called additive. Further facts about biproducts that are mainly useful in the context of additive categories may be found under that subject. As we progress, let's shine a spotlight on kernels and cokernels and examine its intricate interplay within our topic. Because the hom-sets in a preadditive category have zero morphisms, the notion of kernel and cokernel makes sense. That is, if f, a B is a morphism in a preadditive category, then the kernel of f is the equalizer of f and the zero morphism from A to B, while the cokernel of f is the coequalizer of f and this zero morphism. Unlike with products and coproducts, the kernel and cokernel of f are generally not equal in a preadditive category. When specializing to the preadditive categories of abelian groups or modules over a ring, this notion of kernel coincides with the ordinary notion of a kernel of a homomorphism. If one identifies the ordinary kernel Kelvin of f, a B with its embedding Ka. However, in a general preadditive category there may exist morphisms without kernels and cokernels. There is a convenient relationship between the kernel and cokernel and the abelian group structure on the hom-sets. Given parallel morphisms f and g, the equalizer of f and g is just the kernel of gf, if either exists, and the analogous fact is true for coequalizers. The alternative term difference kernel for binary equalizers derives from this fact. A preadditive category in which all biproducts, kernels, and cokernels exist is called pre-abelian. Further facts about kernels and cokernels in preadditive categories that are mainly useful in the context of pre-abelian categories may be found under that subject. Moving ahead, let's uncover the hidden gems within special cases and discover their significance. Most of these special cases of preadditive categories have all been mentioned above, but they're gathered here for reference. A ring is a preadditive category with exactly one object. An additive category is a preadditive category with all finite biproducts. A pre-abelian category is an additive category with all kernels and cokernels. An abelian category is a pre-abelian category such that every monomorphism and epimorphism is normal. The preadditive categories most commonly studied are in fact abelian categories. For example, ab is an abelian category. Your feedback helps me improve, so please take a moment to leave a comment or review.